and look at an example of isotropic hardening. And I guess just quickly, the reason I say isotropic hardening instead of just hardening or something like that is there's another kind of hardening called kinematic hardening. So in isotropic hardening, the yield surface grows only in diameter, right? So we have a stress strain curve, looks like this, and it grows in diameter, okay, as a function of the equivalent plastic strain. There is another type of hardening called kinematic hardening, and in kinematic hardening, the yield surface translates. So if you only had kinematic hardening without isotropic hardening, the yield surface would stay the same diameter, but it would move in stress space. And the reason this causes hardening, especially it causes hardening in one direction, right? Because now if my state of stress is out here, I can still be elastic, but I'm further out here, right? So this actually causes deformation-induced anisotropy. Kinematic hardening does. Because now the yield surfaces can translate around in stress space. It's still a cylinder, but it's translating around in stress space, and that can cause deformation-induced anisotropy. And you can, of course, have combined hardening too, right? So the case of translation, and we're not going to cover it in any detail here. There's just not enough time to cover every possibility. But in the case of translation, the terminology is called kinematic hardening. Okay. So when you have isotropic hardening, we have a yield function that is the square root of 3j2 minus y, except now y is actually a function of the equivalent plastic strain. And so we propose that function for isotropic hardening to be the quasi-static yield stress minus some hardening constant times the equivalent plastic strain. And this is pretty obvious if you just look at a plot, right? Stress, strain. If this guy right here is sigma y, the quasi-static yield stress, and then you have some hardening, this is your hardening modulus, and it's a function of the equivalent plastic strain. So a convenient way, remember, a convenient way, we talked about that F is either less than 0, in which case it's elastic, or it's identically 0, in which case the flow is plastic. And you can actually set up these plasticity problems according to something called the Kuhn-Tucker constraint equations. Kuhn-Tucker constraint equations. And these, if you've ever had a class in optimization, you've seen them, but basically what they are is that F is less than or equal to 0, lambda dot is greater than or equal to 0, and lambda F is equal to 0. Lambda dot F is equal to 0. So this is sort of the mathematical form of the problem we're solving. So we're solving an optimization problem according to these constraints. And you know, it's basically no different than what I've said in words. If lambda dot is equal to 0, then F, according to this equation, then then this is satisfied. So this equation is 0, and then this has to be less than 0. So so it's elastic. Otherwise, if lambda is positive, and by the way, lambda dot lambda, it's always positive. It can't be negative. And so if it's positive, then you have some plastic flow, and you have to satisfy this equation. And it turns out that you can basically combine these conditions to come up with a complementary condition that says that F dot is equal to 0. And so this is really all we need to solve. And so we can do that. I'm going to write this term, instead of square root of 3j2 from now on, I'm going to write that it is 3/2 it's actually the equivalent stress. Remember, I defined the equivalent stress? What symbol did I use? Equivalent? Something like that? Yeah. Okay. So then if we differentiate this guy with respect to time, you just get that the time rate of change of the equivalent stress minus, this is a constant, so there's no change in time, minus h, this guy, and then that's equal to 0. And then we plug in our definition for this, equivalent plastic strain. Remember, that's square root of 2/3 EIJ, EIJ, EIJ. Which turns out to be equal to square root of 2/3 lambda. All right? So we plug that in, lambda dot is equal to 2/3 h lambda dot. And so using this equation and that equation I labeled star, we now have enough information to solve for lambda dot. I'm just going to write down the solution. So lambda dot is equal to E ij Q ij h over 3 mu plus 1 inverse. Yeah. Actually, yes, it should. Actually, it might be a little confusing if you go back in your notes, because go back for a second. Yeah, I didn't use the equivalent stress here. what I did,
You did it the last time.
huh?
You did it the last time, the previous class.
Yeah, I know, but everything's related. Let's just see. It turns out that you can show that this term here is equal to what we'll call like scalar magnitude of S dot. You can show that works out. Right? Where S is equal to Sij. Sij. Okay. I think I'm really not working off my notes here, and I'm sort of using a combination of something. Actually, this is a proposal I wrote, and there's some stuff in here I'm sort of following, but I'm using different notation in here, so this is sort of off the cuff, and I might have made a little mistake. But so let's do this. Let's correct it. Let's rewrite this equation. Eij, Qij minus S dot, where this is understood that that's my scalar, minus lambda dot. Okay. So this is, and it's equal to 0, right? So just remember, I mean, I'm contracting a tensor with a tensor. So this is a scalar, this is a scalar, this is a scalar. Okay. So let's call this star. All right. So this is star. All right. And with that, according to the same definition, I can show that this, instead of being the equivalent stress, it is the square root of 2/3 S. According to the same definition. Okay. And so when I differentiate it, square root of 3/2 S. Okay. And so then when I differentiate it, I have 3/2 S dot. And then I can solve for S dot. So solving this for S dot, let me just write out all the steps. Then, now you can see if I multiply both sides of the equation by the square root of 2/3, if I multiply this equation by the square root of 2/3, then this just, the first thing becomes 1, and this just becomes 2/3. So then I have S dot is equal to 2/3 H lambda dot. Okay. Now I can plug this in to star, right? So now I have an expression for S dot. I plug it in here, and I have an equation that's only in terms, the only unknown is lambda dot. right? Because this is the total strain. We know that at any point. I mean, it's according to some boundary condition. I deform the thing, compute the total strain, right? So then I know it, and I can. So then I can solve for lambda dot explicitly. I have Eij Qij H over 3 mu plus 1 to the minus 1 power. And so lambda dot, this is all things we know. Eij is computed from some boundary condition, some deformation. Qij is the direction of deviatoric elastic stress, right? So I just evaluate the elastic stress, and then I just compute the unit tensor. So it's just a direction, okay? And then I have that, okay? And so with that, do what?
What's after the plus? Is it the plus?
1 plus 1. So with that, I can actually write down my entire constituent model in rate form at least. So now I have that the stress rate is equal to, and it takes a little bit of manipulation to get here, but at K plus 2 mu cubed over H plus 3 mu mu minus 6 mu squared and this is for when F equals to 0, and otherwise it's just elastic. And these should be rates.